Moving charges and magnetism introduction. Learning outcomes of this video are some definitions in this lesson. Force on charged particle in electric field and factors affecting on that force. Force on a charged particle in magnetic field.
Namaste students, this is Chalpati, faculty in physics. Now I am going to explain the topic by screen sharing.
Some physical quantities in this lesson. The first one, magnetic flux. Magnetic flux nothing but the total number of magnetic field lines of force passing through a closed surface are called magnetic flux. It is denoted by symbol phi. Actually, in particularly, it is a magnetic field, so that is why we are indicating with phi b. If it is electric field, then we will indicate as phi e with a particular diagram. So magnetic flux nothing but the total number of magnetic field lines. So here you can see S1 one surface, S2 one surface. So for entire closed surface you can see S1 surface. Through this some number of magnetic lines of force are passing. So here due to magnetic field some lines of force are passing through this. So these lines of force we are calling as flux and unit is Weber. Next one, magnetic flux for a bar magnet. You can see the diagram. So a bar magnet, so here indication of north pole, south pole are there. Now to analyze the magnetic flux due to this bar magnet, we are taking a reference pole. In case of electric field, we will consider 1 unit positive charge as a reference. With respect to that positive charge, 1 unit positive charge, we will give the complete electric flux details. Now in case of magnetic flux, we are taking the reference as 1 unit north pole. Now imagine 1 unit north pole if you place at any point. For example, consider a point here. So here if you place 1 unit north pole, immediately the north pole will repel this one. So then this unit north pole will go away from this north pole. So in this way you should imagine some number of lines. So here magnetic flux means number of lines of force. So here these are magnetic lines of force. Magnetic lines of force means these are imaginary lines drawn in magnetic field in which 1 unit north pole will move. So here we can keep the 1 unit north pole at any place, then with respect to north pole that unit north pole will be repelled and at the same time south pole will attract that pole. So that is why due to our reference north pole, so here towards south pole lines of force are entering. So here in the diagram clearly you can see lines of force means magnetic flux coming out of the north pole and reaching the south pole. This is the information about magnetic flux for a bar magnet. Next, one more physical quantity, that is intensity of magnetic field. It is denoted by H. So intensity of magnetic field at a point in a magnetic field is the force experienced by 1 unit north pole placed at that point. The unit is ampere per meter. Next one, magnetic induction or magnetic flux density. The number of magnetic lines of force passing through a unit area is called magnetic induction or magnetic flux density. So here simply magnetic induction mathematically we can write as flux per area. Here number of lines of force crossing through unit area. So that is why if you observe a diagram here, consider a particular area. The same area if you observe here also, there is a small difference. Here very near to the North Pole, number of lines of force are more which are crossing this area. But if you observe here, the number of lines of force are little bit less. So if you consider the same area very near to the North Pole, very much near to the North Pole, then the lines of force will be much more. The same area if you consider little bit away, for example here if you consider, then the lines of force will be much less. So that means that magnetic induction is more if you consider that area very near to the magnet. As we are moving away from the magnet, or we are moving away from the magnetic field, the flux density decreases. That units are Weber per meter square. Here Weber is the unit of magnetic flux and meter square is the unit of area, so that is why Weber per meter square is the unit. Or the collectively Weber per meter square we are also calling as 1 Tesla. This is MK system of unit, nothing but SI system of unit. In CGS system, the magnetic induction unit is Gauss. So 1 Gauss in CGS system is equivalent to 10 to the power of minus 4 Tesla, or 1 Tesla equals to 10 to the power of 4 Gauss. Next, force on a charged particle in an electric field. For example, a charged particle is there in magnetic field, or it is moving in magnetic field. Number of cases we can discuss here. First of all, to get the idea of force acting on the charged particle in electric field, we should recollect the definition of intensity of electric field. So according to intensity of electric field definition, that intensity of electric field at a point is the electric field force experienced by a unit positive charge placed at that point. As like intensity of magnetic field, here also same comparable definition. In case of intensity of magnetic field, that is force experienced by one unit north pole placed at that point in magnetic field is the intensity of magnetic field at that point. Similarly, intensity of electric field at a particular point in electric field is also same. Force experienced by one unit positive charge placed at that point. So here 1 unit positive charge we are taking as a reference, that we are indicating with charge Q. Now according to that definition, we can say intensity of electric field E equals to F by Q, force experienced by 1 unit positive charge. So in general we are mentioning as a symbol Q. So with respect to that, F equals to EQ. Further, we can analyze the force experienced by the charged body. So in general we defined for a particular unit charge or particular quantity of charge also we can give the expression same way, F equals to EQ. Now the factors affecting the force. So clearly according to the formula you can say, if that electric field intensity is high, then force on the charged particle is high. And one more, if the magnitude of charge is high, then also force is high. Why? Because here the force is proportional to electric field as well as proportional to charge, means magnitude of the charge. The force on the charged particle depends on the magnitude of the charge and as well as intensity of electric field. Next, one more major point we should study, that is the direction of electric field. This is always in the direction of electric field. If you consider a particular diagram, it will be very clear. So consider electric field in between two metal plates. For suppose this metal plate is positively charged and here it is negatively charged, then definitely in between the two metal plates there will be a uniform electric field pointing from positive charge to negative charge. Here electric field direction from positive to negative. Now for suppose there is a positive charge inside the electric field, then definitely there will be a tendency to this positive charge to move towards the negative charge. Why? Because here this negative charge will attract the positively charged body. Similarly, negatively charged body will get the tendency to move towards the positive charge. That means here the negative charge will attract by the positively charged. Now if you see, this positive charge is moving towards negative charge, means it is moving in the direction of electric field. So for the positively charged body, the force direction is along the direction of electric field. But in case of negatively charged body, it is attracting towards the positive charge, means it is opposite direction, means direction of force on a negatively charged body is opposite direction to the intensity of electric field. Now next important point, when a charged particle enters the electric field in a direction perpendicular to the electric field, it follows a parabolic path. If you observe this diagram, there is an electric field in between the metal plates. You can see here positive charged plate, negatively charged plate, electric field from positive to negative. For suppose a negatively charged body entering into the electric field perpendicularly, then whenever it enters into the electric field, then there will be a force acting on this charged body. That force is always, it is a negatively charged body, always towards the positively charged plate. So due to continuous force, this negatively charged body will not follow a straight line path. So it will move continuously according to the dotted line path. It will not follow a straight line. Reason, there is an electric field. So for that, if you consider x-axis and y-axis, for example, the charged particle moving along x-axis and electric field along y-axis. So continuously along the y-axis, means along the negative y-axis, electric field along the y-axis, but electric force on this charged particle along the negative y-axis. So due to that there will be an acceleration. So due to that acceleration, the displacement of that charged body, you can say, as according to the formula s equals to ut plus half at square. So here initial velocity along the direction of electric field is 0. So it is moving along x-axis. So along y-axis there is no velocity to this charged particle initially. So that is why initial velocity is 0. So then we can analyze this expression as s equals to half at square. So here a is the acceleration on this charged body due to the electric force. So that is a constant value. So the displacement of the charged body due to the electric force acceleration is proportional to t square. So here this formula is indicating that as like y equals to kx square, means it is a parabola equation. That means the path of the charged particle in electric field, if it enters perpendicularly, then it will follow a parabolic path. Next topic, force on a charged particle in a magnetic field. If a charged particle of magnitude q is moving in a magnetic field for suppose capital B with a velocity v, then the force on the charged particle we can express as F equals to q into v bar cross b bar. Here velocity is a vector and b is also a vector, magnetic field direction, so it's a vector. So here v cross b we can also mention like this, that is, it's a cross product between two vectors, nothing but vb sin theta. So here some factors affecting the force, those if you analyze, first one theta. So here theta is the angle between the velocity and magnetic field, velocity of the charged particle and magnetic field. Now if you analyze point wise one by one, the force on the charged particle depends upon, according to the formula, F equals to QVB sin theta, the factors one by one. Magnitude of the charge will affect the force. If magnitude is high, then force on the charged particle is high. For example, the parameters velocity, magnetic field and theta, if those are all constant, then as compared with force on electron or proton, the force on alpha particle is high. Why? Because alpha particle charge is greater than the proton charge or electron charge. So that is why force, I am talking about only force, magnitude irrespective of the direction. So if charge is high, definitely force on the charged body is also high. Next, it depends upon velocity. So velocity of the charged body. So in case of electric field, there is no effect of velocity. Electric field force is independent of velocity of the charged body, but in case of magnetic field, the force on the charged body depends upon velocity of the charged body and as well as magnitude of the magnetic induction, and one more, that is angle between the direction of velocity and magnetic field. So if the angle is very small, for example if angle is 0, then force on the charged particle is 0. That means if the charged particle moving in the direction of magnetic field, velocity vector of the charged particle and magnetic field vector of the magnet, if both are parallel to each other, then theta is 0. If theta 0, sin 0 0, then force on the charged particle is 0. Next, the direction of magnetic force is always perpendicular to the both magnetic field and velocity. So for that, if you observe the diagram, for example, a charged particle moving along the direction as shown in the figure, that is for example in this direction, and magnetic field is also there in the particular direction. For example, both are in a plane if you consider, then the force direction is always perpendicular to the plane containing the velocity and as well as magnetic field. The direction we can specify, in particular it is simply the normal to the plane, that we got reason. Here it is a cross product between the velocity vector and the magnetic field vector. So for that, just consider your right hand. That right hand try to arrange in the direction of, means the palm of the right hand is aligned in the direction of velocity, for example if you keep, and afterwards if you close your fingers towards the magnetic field, then the thumb indicates the force direction. For positively charged particle, the thumb will come in the direction upward. So for negatively charged body it is opposite direction, so it will be downward to the plane. The same thing we can analyze with another diagram also. For example, magnetic field is there upward, and for suppose a charged particle at a particular moment, this is the direction. Then now also you can analyze same like what I said with the right hand grip. So keep your right hand fingers pointing the direction of velocity, and afterwards close your fingers towards the magnetic field. So here your fingers align it to the magnetic field, afterwards you have to close towards the magnetic field. Then the thumb indicates the direction towards the center of the circle, what is shown in the diagram. Means as a charged particle is moving perpendicular to the magnetic field, here you can see the charged particle is moving perpendicular to the magnetic field. So continuously the charged particle will move along the circle. That is the major point. So further much more details are there about this force on the charged particle in magnetic field. We will discuss in the next class. Thank you.